In this video, I want to have a look at rates of change. So we have sort of started having a look at this when we were talking about motion and velocity and acceleration, but we want to look more generally at just other things that are changing, not necessarily a particle moving. So a rate of change refers to the instantaneous rate at which a quantity, called q, changes over time t. So the rate of change is the derivative dq dt, so differentiate q with respect to t. Now, we don't always use the letter Q. If we're talking about, say, a population changing, we might use P instead, or a volume, we might use V, or any other letter that represents the situation. So let's have a look at an example. Our first example says the mosquito population is represented by P equals 900 plus 20t minus 0.2 t squared, where t is time in days. Part A asks us to find the initial mosquito population. So when we're talking about initial, we're saying when t is equal to 0. So we're going to find p when t is equal to 0. So we'd have 900 plus 20 times 0 minus 0.2 times 0 squared, which would just give us 900. So the initial mosquito population was 900 mosquitoes. For part B, it asks us the rate of at which the population is increasing after 1 week. So this is part B. So because we're talking about a rate, we are going to have to differentiate. So if we differentiate P with respect to time, then we'll end up with 20 minus 0.4t. Now we want to know what this rate is after 1 week. Now t is time in days, so we're going to find the rate when t equals 7. So when t equals 7, dp dt is going to be 20 minus 0.4 times 7, which would give us about 17.2 mosquitoes per day. Part C asks us to find the maximum population. So if we're talking maximum, we want when the stationary points are, so we want when this rate is equal to 0. So we're going to put 20 minus 0.4t equal to 0, which would mean that 0.4t is equal to 20, which would mean t is equal to 20 divided by 0.4, which would give us 50. So this tells us when that maximum occurs. We do need to check that it's a maximum. So to do that, you can either substitute a value in on either side of that 50 into the first derivative and see what the gradient is, or you can substitute into the second derivative. So I'm going to do that. So d squared p dt squared will just give us minus 0.4. So that means that our curve is always concave down. So that shows us that this is a maximum. But that, again, that only tells us when the maximum population occurs, not what the maximum population is. So we're going to find p when t equals 50. So p would be 900 plus 20 times 50 minus 0.2 times 50 squared, which would give us 1,400 mosquitoes as the maximum number of mosquitoes. Now, our second example is a little bit different because it actually gives us the rate, not the original equation. But let's have a look at what the differences are when we're solving a problem involving the rate. So a bathtub initially holds 180 litres of water. The rate that the water drains from the bath is given by dv dt equals minus 45 outside of 1 minus t over 8, where t is time in minutes after the plug has been pulled. So part A asks us what is the rate, at what rate is the water initially draining? So again, that word initially means when t equals 0. So when t equals 0, the rate, which is dv dt, we're just going to substitute 0 in here. So we'll get minus 45 outside of 1 minus 0 over 8, which will just give us minus 45 litres per minute. So the minus 45 is because the water level is decreasing. For B, it says how much water is left in the tank after 5 minutes. So because we're talking about the volume of water or the capacity after 5 minutes, we don't want the rate anymore. We want to go back to our original equation. So we're going to have to integrate this. Now there's two ways you can do it. You can reverse the chain rule, or we could expand out and then integrate. So it's up to you which way you do it. If we reverse the chain rule, we'd have minus 45, 1 minus t over 8. Now that would have to become a squared, which would mean we'd have to compensate by dividing by 2, we'd also have to divide by the derivative of what's inside the bracket, which in this case would be minus 1/8. So I'm going to write that as divided minus 1/8 over here. Now, if we simplify all that, it'll give us 180 outside of 1 minus t over 8 squared. All right, so this is our volume over time, but we want after 5 minutes. So we're going to say at t equals 5, v is equal to 180 outside of 1 minus 5 over 8 squared, which is going to give us about 25.3 litres. So that's rounded to 1 decimal place. All right, part C asks us when the bathtub will be empty. So for part C, we're going to use this equation here, but we're going to set v equals 0. So we're going to have 0 equals 180 outside of 1 minus t over 8 squared. Now, if I divide both sides by 180, I'll have 1 minus t over 8 squared equals 0. Then if I take the square root of both sides, 1 minus t over 8 still equals 0. Then I can rearrange that to get t over 8 equals 1. And finally, t equals 8. So the bathtub will be empty at t equals 8, so at 8 minutes. All right, so that's having a look at the two different main sorts of problems that you can get involving rates of change.